Hello and welcome. Have you ever been on a roller coaster and felt that intense pull in a super sharp turn? Ever wondered if you could put a number on just how bendy that track is? Well, today, that's exactly what we're going to do. We're going to break down the calculus concept of curvature and turn that feeling you get in your stomach into a real, solid number. So let's just start with that basic question. How bendy is a curve? I mean, we all intuitively know the difference between a long, straight highway and a hairpin turn on a mountain road, right? One has basically no bend, and the other has a really, really tight one. The question is, how do we actually measure that mathematically?
And this visualization just nails that idea. Over on the left, you've got a small, tight circle. That's high curvature. Think of it as that hairpin turn. Then on the right, you see a huge, gentle circle. That's low curvature, kind of like a big sweeping off-ramp on the freeway. It's that simple. The tighter the turn, the higher the curvature.
Now, in calculus, we give this bendiness an official name, curvature. We usually represent it with the Greek letter kappa, which you see here. And what it is technically is a measure of how fast a curve's tangent vector changes direction. Just picture the tangent as the direction your car's headlights are pointing at any given second. If you have to yank the steering wheel hard, that direction is changing super fast, and that means you've got high curvature.
To really help us see this at any point on a curve, mathematicians have this awesome tool called the osculating circle. I love this name. It's also called the kissing circle. Why? Because it just barely touches or kisses the curve, and it shares the exact same curvature at that one specific point. And here's the key thing to remember. A sharper turn is going to have a smaller kissing circle, which means, you guessed it, higher curvature.
Okay, so we've got the concept down. We get the idea of the kissing circle. But how do we get an actual number out of this? For that, we need to open up the mathematician's toolkit. Let's take a look at the formulas that let us calculate this thing for real.
All right, first up is the big one, the general vector formula. I know, it might look a little scary, but it is incredibly powerful, especially for curves moving through three-dimensional space. It uses the first and second derivatives of our position vector, r of t. And hey, for any students watching, here's a pro tip. This version with a cross product is almost always the easier one to use when you're doing your homework. Trust me on that one.
But if our curve is just a simple two-dimensional function, the classic y equals f of x, we've got this specialized formula. It's a lot more direct for those plane curves, and we're actually going to put this one to work in just a minute.
Okay, enough with the theory. It is time to get our hands dirty. In this next part, we're going to go from simple lines all the way to parabolas, and really put these formulas to the test with three totally different examples.
Let's start with the absolute most basic case you can imagine. What is the curvature of a perfectly straight line? I mean, our gut feeling tells us it should be 0, right? There's literally no bend at all. So let's use the math to prove it.
So we start with our general vector equation for a line. In step 1, we take the first derivative, r prime, and we just get a constant vector. Now step 2, and this is the whole game right here. We take the second derivative. And of course, the derivative of any constant is the 0 vector. So when we plug that into our formula in step 3, that cross product in the numerator just becomes 0. And, well, 0 divided by anything is just 0.
And there it is. The math perfectly confirms what we already knew in our heads. The curvature of a straight line is exactly 0. No bend, no curvature. Simple. Okay, on to our next example. A circle with some radius, let's call it r. Now, unlike a line, a circle is always turning. So what do you think its curvature is going to be? It should be some constant value, right? But what is it? Let's find out. We just follow the same process. Step 1, find those first and second derivatives. Then for step 2, we compute their cross product, which works out really cleanly to a nice constant vector. Step 3, we find the magnitudes we need for our formula. And finally, step 4, we plug everything in. R squared on top, r cubed on the bottom, and that gives us our beautiful, simple result.
So the curvature of a circle is just 1 over its radius, r. And this just makes perfect sense, doesn't it? It connects right back to our first idea. If you have a massive circle with a really large radius, r is a big number. That makes 1 over r a small number, which means you get a very gentle curve, or low curvature. It all fits together. All right, for our last example, let's tackle a parabola. Specifically, y equals x squared. Now, here's the fun part. Unlike a circle, the bendiness of a parabola actually changes. It's super tight at the bottom, at the vertex, and it gets straighter and straighter as you go up the sides. So we're going to calculate its curvature at its tightest point, right at the origin, where x equals 0.
Since this is a simple y equals function, we get to use that second, easier formula. For step 2, we find the derivatives. The first derivative, f prime, is 2x, and the second derivative, f double prime, is just the constant 2. In step 3, we plug in our target point, x equals 0. After that, it's just a matter of plugging those numbers into the formula in step 4, and it all simplifies right down to our answer.
So at its very tightest point, the vertex, the parabola y equals x squared, has a curvature of exactly 2. That is the point of maximum bend for this curve.
Okay, so we've done the calculations for a line, a circle, and a parabola. Let's take a step back now and look at the big picture, just to see what these numbers are really telling us. This table really sums it all up nicely. For the straight line, feature no bend, curvature 0. For the circle, feature a constant bend, curvature 1 over r. And for the parabola, at its tightest point, the vertex, we found a curvature of 2. You can really start to see this direct link between the geometry of the curve and the number we get from the formula. So what should you really take away from all this? Well, first, the curvature, or kappa, isn't just a vague idea, it's a precise number for bendiness. Second, a straight line always has a curvature of 0. Third, a circle with radius r has a constant curvature of 1 over r. And finally, and this is maybe the most important point, for most curves that you'll run into, the curvature value actually changes depending on where you are on the curve.
So we'll leave you with this final thought. We've just unlocked a mathematical tool that lets us assign a specific number to the shape of any path. So the real question becomes, now that we can measure a curve so precisely, what kind of complex paths in physics, in engineering, maybe even in computer animation, can we now start to describe, predict, and understand in a whole new way?